Okay, so today we're going to be starting on the next topic, which is searching and sorting. And this is a pretty fundamental topic to computer science, to data science, to whatever you want to call basically processing data. There are lots of disciplines that use this. I mean, even if you're a business major and you're processing data from an Excel file or something like this, you generally have to have some fundamental organization of your data. You have to, and you'll be searching through your data. You'll be and you'll be sorting data to look at the top hits or something like that. So processing data is fundamental to basically any discipline that has data that needs to be processed. And two fundamental operations to processing data, again, are searching and sorting. They form the basis also of many pre-processing algorithms. So typically when you run an algorithm, you have an assumption that, all right, well, give me the input and sorted so that I can go ahead and go through it in this order. Given a graph, you want to create what's called a minimum spanning tree or something like that. You'll assume that the edge weights that you're given are in order, right? It's fundamental to a lot of different algorithms to already have your data pre-sorted or as some sub-steps to some other operation to have it sorted. So these are two very fundamental operations, and we're going to cover in depth how to several algorithms for both, but also how to do it in practice. In practice, you don't reinvent the wheel. Every single programming language out there has in their standard libraries ways to search and ways to sort. To understand how to use them, you need to understand a couple of fundamental things that are almost invariant across a lot of different programming languages. And so we'll look at how to do that. You don't reinvent the wheel every single time you want to sort something or sort it differently. Just imagine like our student structure that you've seen in a previous lab or in a previous lab and in lecture. How do you sort students? You could sort it by last name, first name, right? You could sort it by NUID, ascending or descending. You could sort it by GPA, ascending or descending. You could sort it by last name, first name, and then if they're the same, you could then break ties by NUID. So there are lots of different criteria that you could use. Are you going to write a sorting algorithm every single time you want to sort it a new way? No, you don't. You don't reinvent the wheel. Instead, you use one sorting algorithm, one sorting algorithm, one search algorithm to rule them all. You have one thing that you use, and then you configure it to do different things. There are a variety of algorithms that have been developed, and we'll look at a few. But of course, we'll go ahead and start with searching first. So the fundamental questions you have to ask yourself before you start this are, what are you searching? Sorry, did I say sorry? Did I say we're going to start with searching first? What are you searching? Are you searching strings, numbers, files, objects, right? Those are very practical questions. That's a very practical question with very practical answers that you need to know, because if you're actually going to do some data processing, well, what am I actually processing here? And then how are you searching, right? And I'm not talking not algorithmically here, instead, but by what criterion? Criteria or criterion, right? For example, the student structure that I just talked about. You could be searching for NUID, you could be searching for last name, you could be searching for GPAs, but also more generally, you could be searching for the first or the last or all instances of a particular element or criterion. Criterion, right? Or criteria if you want to look at multiple criteria. Which one do you want? Search through an array or search through a collection, and the first one you find, that's good enough, right? Or maybe you want to find them all. Find everybody whose GPA is at least 3.5, because then we'll put them on the dean's list or something like that. There are lots of different variations here. You could search for extremal elements, and you've already done this. Minimum, maximum, median, or more generally, in your third homework assignment, you search for the ith order statistic, right? Those are all extremal elements, and you want to find the 75th percentile or something like that. What's the cutoff for that? Meaning that 2/3 are below that, and then 3/4 are below that, and then 1/4 is above that. That's the one you're searching for, not just the max or the min or something like that. And there are many basic, many other basic and advanced criteria that you can search on, right? So I don't want to have to worry about this. If you are actually solving a problem, you're going to have to answer these questions. Exactly what we're searching for, exactly how we're searching for it. But what I want to do is I want to solve this problem generally. I don't want to have to worry about whether or not we're searching for strings or numbers, and that we're searching for all strings or all particular numbers. So what I want to do is I want to formulate, at least as a first step, we want to develop a general abstract search algorithm. Right? This means that we're no longer going to be programming, at least initially. What we're going to be doing is we're going to be developing this through pseudocode. Pseudocode. Right? So what does pseudo mean for those of you who out there speaking Latin? Pseudo is fake, right? It's fake code. Pseudocode is a generic code language that allows you to specify a general abstract algorithm without getting into the specifics of any particular programming language. Okay? So there are no rules for pseudocode. Guess what? If you had rules for pseudocode, what would you have? A programming language, right? Programming languages are the ones that require hard and fast rules, syntax, grammar, stuff like that, punctuation, in order so that the compiler can actually compile it into a runnable program on a computer. There are no such rules with pseudocode, so we'll often use mathematics. We'll use plain old English. We won't have to have particular language elements like, say, opening and closing curly brackets or semicolons at the end of every executable statement. It'll look very much like code, but it's not going to be exactly code. And the purpose of this is that you want to describe this abstract process, this algorithm, which you can then, it's just a general idea of how you approach this problem, how you solve this problem. Then you can take that algorithm and you can translate it to C. You could translate it to Java. You could translate it to Python. Once you have this abstract solution, then you can start translating it to an actual programming language. Okay? And that's what we're going to do now. So for that, though, I'm not going to be able to program it on the screen here because it would not look good in Markdown. So what I'm going to do instead is I'm going to switch over to the .cam here, and let's develop an algorithm. Hopefully it focuses. If not, let me know. And it should still pick up on the video. It's recording what's on screen, not what's on my computer. So what we're going to do is we're going to develop an algorithm. We're going to develop it through pseudocode. The idea here is, let me go ahead and start with identifying the input. All right? The input to this algorithm is going to be a collection of elements. And I'll give that collection a name. A1, A2, ... AN. Right? And a key element. K. Okay? This is this is very well thought out pseudocode here. In that it looks kind of like a program. Like if you were to write a function, your function has parameters. It has input parameters, right? But you don't specify what they are. Here's an array, and here's its size, and here's a key element, right? I didn't do that here. I did specify the size. But one thing I didn't do is I didn't start my indexing at 0 because I'm using more mathematics here. Right? I'm keeping this at a high level. Computers, most programming languages, use 0 indexing. There are some programming languages that do not, and certainly in mathematics, I've never seen a mathematician start their indexing at 0. So I'm going to keep it abstract by starting it at 1. I also didn't specify that it was an array, or that it was const, or that it was an array of integers. It's a collection of elements. What are those elements? Strings? Numbers? I don't care. I'm solving a generic, general problem here, right? And a key element, k. What we're going to do is we're going to search through this collection here and find any element that matches the key element here. And so that's what I'm going to output. I'm going to output an element, and note here I'm using plain old English, an element a sub I in A such that a sub I is equal to k. Now again, I'm just using plain old mathematics here. It wasn't equals equals because that would imply that they're numbers. If they were strings and I was using C, then I would use strcmp, right? There's no such specification here. I'm keeping this general. When you translate this over into an actual program, then you would need to specify those things, okay? And I'm going to leave myself some room here. So you actually all did this already in your third programming assignment. You just didn't do it pseudocode way. You all had to write functions that given an array and given a key element, we didn't call it a key element, but given an element, you had to search through and answer, yes, that element is in that array, or no, it is not in the array. You return true or false. What we're doing here is we're actually outputting the element that matches to it, okay? We could change this when we translate it into an actual program. We could change this into a Boolean function that returns true or false. Yes, it's in there. No, it's not. Or we could translate it into a function that returns the index at which it finds it, right? Or we could translate it into a function that returns a pointer to it. There are lots of options here. This is going to be kept general, though. So what's an idea here? How are you going to search through these elements and find, we usually refer to this as the needle. This is the haystack. You're searching for a needle in the haystack. So how would you go about this if it were C? A for loop, right? So I'm going to do that too. For each element a sub I in A, I'm going to go ahead and compare it. You can use for statements here, but I'm using plain old English along with a mixture of mathematics here. If a sub I is equal to k, you could even use parentheses if you want, but it's not absolutely necessary. If you found what you're looking for, what are you going to output? The output is an element A that matches it, so if I find an element that matches it, I will output it, right? I'm not, I went into Python mode here for 1 second and put a colon there. Let me go ahead and ignore that, but it's a pen, so I can't erase it. I didn't have opening and closing curly brackets here. Instead, what I like to do is, this is because this is from LaTeX, I like to put in vertical lines down here because there's no way that you are reproducing that in an actual coding language. If you were to use LaTeX and typeset this, you could get that effect. But this is a real huge departure from anything that you can do in actual code. I didn't have opening and closing curly brackets here because that would be C-style syntax. You do that in Java, you do that in PHP, you do that in C, C++, C#, et cetera, et cetera, et cetera. But there are some languages that you don't do this. One I just mentioned, Python. Python does not use opening and closing curly brackets to denote code blocks. Instead, it relies on indentation, which is actually far worse, and you pay for it. But it would also have colons to specify that this is what should happen in this for loop. That looks pretty good, except for what? What am I assuming here? I'm assuming that I'm going to find my needle in the haystack. What if I don't find my needle in the haystack? Is this if condition ever going to be satisfied? Nope. So, an unsuccessful search. What do we do? In the version that you wrote for assignment 3, you returned false. This is different. I'm returning an element instead. What could I return instead? I could return 0, right? Or maybe if it was C, I would return null. But those are programming language concepts. Some languages don't have null or try to eschew null or try, like C# has tried to get rid of null for a while and they've got optional now, and Java's kind of doing that as well. But this is just plain old English. This is plain old English and mathematics. What I'm going to do is I'm going to steal a term from math. An element, if it exists, or this if no such element matches. All right, so I asked you about Latin. Nobody said yes, but certainly on a college campus, you know what this is. What, it's a Greek letter. No? Not well versed in Greek? Okay. That is a lowercase phi. Maybe because you're used to seeing it like that. All right, that's uppercase phi, right? Whatever. All right. It's a lowercase phi. It's just a symbol to denote a flag, right? If you were doing this in C, you could use false, you could use 0, you could use null, you could use a lot of different things, right? But I'm going to use phi. So if I get out of this loop without ever finding a match, oops, I went back into code mode there. I'm going to output phi. Right? Now note here, no semicolons. Again, no code blocks are denoted not with opening and closing curly brackets. But also, is this a function? Am I returning something? No, it's just an algorithm. So I'm outputting something, right? And that's the end of the algorithm. The algorithm either ends here or it ends here. That's some pretty good pseudocode for an algorithm called linear search. And this is a pretty straightforward algorithm here. It's brute force. It is exhaustive. Sometimes it's called exhaustive search. You just search. You start at the beginning. You start searching until you find what you're looking for, and that's it. Okay. You can take this and translate it to any programming language of your choice. Let's do that. Right? So hopefully you've got that seared in your mind. Because we will be going back to the computer here, okay? So, linear search, pseudocode, see video, or no, you know what? See the book. It's in the book if you want the in whatever chapter you're supposed to be reading this week. I forget the number. But let's go ahead and translate. Let's translate the linear search algorithm into actual C code, right? Okay, so some suggestions here. We'll go ahead and write the documentation so that we know what we're talking about here, but we won't actually complete it until we've decided how we want to design this function. This function searches the given array for the given key value and returns ... I don't know what we're going to return yet. I don't know how to design this function because we just had a very general, very abstract description of this algorithm. What I want to do now is actually make it into a concrete implementation. I will call it linear search. Okay. And now let's develop this. So let's answer those questions that I posed before. What do you want to be searching? Let's just make it easy. Let's search for through an array of integers, like you've done before. Int star ARR, int n for the size. Now, are you going to be making changes to this array? Nope. So let's go ahead and make it const. Right? So there's my array. There's my collection. There's the size. I have to do this because it's in C, but over here in my pseudocode, I gave it a label, so I don't have to do something like that. And then, of course, I'll need to be searching for a key value. Int key. And those types have to match because if you're searching a collection of integers, well, your key has to be an integer. You can't search a collection of numbers searching for a string. You can immediately say, no, I'll never find it, right? So, given the key value and returns what? What should our return type be here? Let me go ahead and start you off with maybe an int, okay? But what is that int going to represent? So here's a collection, here's an array of elements 10, 20, 30, 40, 50. Right? Here's your 5 elements. I want you to search through there and find 20. Okay, 10, or let's say that I want you to search for 40. 10, nope, that's not it. 20, 30, 40. Oh, I found what you're looking for. It's 40. Did I give you any useful information there other than, yeah, it exists in there? Right? What more information could I give you? The what? the index at which I found it. Because I've already got 40 over here. I don't need to know 40. That's the key value. So let's go ahead and suppose that the return value here returns the index. In fact, the first index at which at which it finds a matching element. Right? Good. We'll come back to that because we still have some questions to answer here. So this is pretty straightforward, right? A for each loop. Well, we don't have for each loops, but we do have for int I equals 0, I is less than n, I plus plus, right? Very idiomatic for loop to iterate over a collection, iterate over an array of size n. And we've also got if statements. If the ith element is equal to the key element, then I will return. Oh, what do I return? I return the index at which I found it, which is I, right? What do I return for an unsuccessful search here? What if I return 0? What's that? What does that say? I found it at index 0, right? So what's a flag value that would indicate that it's not in there? Because if it were in there, I would have told you 0, 1, 2, 3, or 4. Yeah. Okay. -1? All right, that works for me. Right. We'll put that into our documentation as well. This function returns -1 if no matching element is found. This gives you twice as much information as before. Because not only does it tell you that it's in the array or it's not in the array, but it tells you that if it's in the array, here's where it's located. Right? What's an alternative that we could have done here? Instead of returning an integer, what if let's just look and see what it might look like. Let me go ahead and cut and paste this, bring it down here. Here's alternatively, right? What if instead I said, okay, what if we return a pointer instead? I'm not just going to tell you the index at which I found it, but I'm going to point to where I found it. What would that look like instead? You'd go through, you would find a matching key, and if you found the matching key, you wouldn't return the index, you would return what? Ampersand a sub I. The a sub ith element, that parameter, the square brackets there, dereferences it, so it's a regular variable then, and I need to have a pointer to it, so I put an ampersand in front of it, and I return that. What about -1 though? -1 is not any memory address that I've ever heard of. So what's a memory address flag value that can indicate I didn't find it? Null. Sounds good to me. Right? So this is an alternative. Right? There are lots of different ways that you could do this. You did a different variation in your assignments, that you returned yes or no answers instead. You can design it like the first one. You can design it like the third one, right? Or you can design them all and then give them different names because you want to use them. You want to use them in different ways, right? All right, good. That was a good exercise that we translated some pseudocode into an actual program. Right? But there is a problem with either one of these. The above functions are only good for, well, what are they good for? They're good for arrays of integers. Arrays of integers, right? If we wanted a version for arrays of doubles or char star strings, right? Strings, or maybe student structures, etc. What would we have to do? What would you have to do? Take that function, cut, paste. What would you change? Let's take the second version here. You would change, well, now it's a double array. Well, let's just say doubles instead. Now it's a double key, right? What else? That's it, right? Nothing else would change in that function. So does that sound like a great idea? Cut, paste, just change the, and of course I would also have to change the name because you can't have functions with the same name. That goes all the way back to function overloading. That's why you need 3 or 4, a dozen absolute value functions. Yeah. Oh. Sorry, go ahead. It's returning, oh, sorry, it would be returning a double pointer. Yes, thank you. Right. Was that your question? Oh, okay, yeah, go ahead. No, because the size of an array can't be 3.5, right? That's still the size, right? All right, so does that sound like a good design principle? Cut, paste, modify, cut, paste, modify, cut, paste, modify? Probably not, right? Our ultimate goal, eventually, is to design and implement one search or sort function to sort or search and sort any type of variable. And in fact, we're not going to end up reinventing the wheel ourselves. Instead, we're going to use what's already in the language. Okay? But before we get there, let's go ahead and look at an alternative here. I'll go ahead and give you the name. It's called binary search. Okay? Can we go before we worry ourselves about rewriting this and thinking of another or a better way of doing this in C? Let's think about doing it in a better way in pseudocode. Right? Is there a better search option? Suppose that the input array were or collection were sorted. Right? How can you exploit this structure? Right? So for that, I'm going to again go back to a nice picture here, or at least a hand-drawn picture. I can't guarantee that it's going to be pretty. .cam. There we go. All right, and look. So if you had an unsorted array, the linear search algorithm that we just developed, that's your go-to. You're going to have to exhaustively search everything. But what if you had an array that looked like this? 0, 2, 4, 4, 10, 1, 2, 3, 4, 5, 42, 79, 5, 6, 7, 8, 9. Okay, so 101 and 200. All right? Now, that's your array. I'm not going to draw it as a complete array here. But let's suppose that you wanted to search for 101. Now, if you use, it's right there, right? So as a human, you can look at that. Yeah, it's right there. But a computer can't do that. A computer has to have a specified routine for systematically going through stuff and finding what you're looking for. So if you started out with that linear search algorithm, what would you have to do? I would look here. I would make one comparison, say, nope, that's not it. Nope, that's not it. Nope, that's not it. Nope, that's not it. I've got now 4 comparisons. 5, 6, 7, 8. Oh, I found what I'm looking for. I found the needle in the haystack, making 8 comparisons. All right? But it's sorted. How could we exploit that fact? What I'm going to do is I'm not going to start at the end. I'm not going to start at the beginning. You might be tempted to say, oh, well, 101, why didn't you start from over here? Because then you do 1, 2 comparisons. Right? Well, a computer can't look ahead and make that kind of prediction. And besides, what if instead your strategy was to go from this end? Well, what happens when you want to search for 2? Then you'd have to make 8 comparisons to get all the way over there. Right? So what I'm going to do is, since it's sorted, I'm going to look in the middle. There are 4 elements, so the middle here is this guy, 10. Okay? And I'm going to compare it to 101. 101 is bigger than 10. So what does that tell me about this half of the list? Or this half of the array? It's not there. It's irrelevant. Throw it away. Right? Well, before you do that, you make a comparison to 10. Is it equal? Did you find your needle in the haystack? Nope. So you need to look at, well, if I'm only looking at this, then I can determine 1 or 2 things. Either it's equal, in which case I'm done. I found what I'm looking for. Or I say, oh, well, I need to search on this end, or I search on this end. because everything over here is greater than 10. Everything over here is less than or equal to 10, or strictly less than, whatever, however you want to look at it. In either case, what have I done to my array of size 9? How big is the section now that I have to start searching? It's only 4 in this case, but in general, it's going to be half as big, right? So I will repeat this process on the right-hand side, right? We call these partitions, right? So let's repeat 42, 79, 101, and 200. Now, there's no definable middle here. Let's say that 79 is the middle. This is the middle because there are roughly about half the elements over here, half the elements over here. If you've got an even number, you're not going to have an exact split. So let me go ahead and just say, suppose that that's my middle. Okay? All right. Well, 101 is greater than 79. So what can I do now? I can throw out this element. And I only need to look at, again, the right partition. When I recurse, oops, I gave it away. Spoiler. What am I doing here? I'm recursively solving this problem, right? And so I'll look at the middle again. Maybe that's this. And oh, now I'm done. Right? How many comparisons did I make to make this determination? 1 to say that, that's not equal and I need to go over here. 2 to say that this is not equal and to go over here. 3 to say, oh, I found my needle in the haystack. I only need to make 3 comparisons by exploiting this structure, right? More in general, if you want to look at it from another perspective here, is that if you look at the middle element m here, everything, since it's sorted, over here is less than m. Everything over here is greater than m. So all you need to do is check, does it equal m, right? Is my key equal to m? If so, then done, right? You're just output that element or the index at which you found that element. Otherwise, so if the key element that you're searching for, in this case the key element was 101, if the key element is less than m, then you search in the left side. Otherwise, if the key element that you're searching for is greater than m, then you search in the right side. Okay? When do you know that you're done? Well, we got done on this one because we were successfully searching for it, 101. What if instead I were searching for, say, 3? No, I want something else. Say 5. What if I searched for 5 in this example here? I would look at 10 and say, oh, that's not equal, so I would recurse on this side. I would look at the middle and say 2, okay, that's not equal. I'll recurse on this side. Now I've just got these 4. 4, okay, that's not equal, so I would recurse on this side. 4, that's not equal. I would recurse on, how big is my array now? 0, right? So you stop when either 1, you found your needle, or 2, your array size is 0. Right? Because certainly, if I gave you an array of size 0, can you tell, and I asked you, oh, well, is 10 in there? What would be your immediate answer? No, nothing is in there. Right? So that's the idea behind this binary search here. Okay? Yeah?
Could you do this if you were looking for the first instance of something? If you landed on
Correct. So what if you were searching for 4, right? Which one do you want? Then you've got some thinking to do there. Once you've found 1, though, you can just go left and right and find them all, right? So in general, the solution that we're going to be preferring is any one of them is good enough. Right? The first one that you find, first as in the first in the process, not the first as in the first in the array. You could find this one first, but it's not the first element. Right? Okay? So that's the idea. Let me go ahead and switch back here, and let's codify this, at least in some notes here. All right? So the idea is that you can exploit this structure. You can exploit this structure by checking the middle element. Right? Either 1, if equal, you stop because you've found your needle in the haystack. Otherwise, if by checking the middle element. say I'll give this a name, M. You are searching for K, right? Let's say. So if they're equal, in other words, M is equal to K, then you stop because you found what you're searching for. Otherwise, if the key that you're searching for is less than M, then you recursively search on the left-hand side, right? If, let's say, M is less than K, or K is greater than M, if you want to look, either way that you look at it, you recursively search on the right-hand side. Right? So that's the idea. You stop. All right, let me go ahead and put it that there. You stop when the size of the array is 0, right? Because there's nowhere else to search. And then you can return false. You can return 0. You can return null. Whatever implementation that you're actually doing. Or if it's an index-based find, you can return -1. Okay. Let's see. Yeah, let's go ahead and implement this. I want to make sure that it works, so let me go ahead and fire up REPL here. Unfortunately, I didn't prep some good test cases here, so bear with me. Let me go ahead and create at least an array, int arr equals to, by the way, it has to be sorted. If it's not sorted, you can't exploit that structure. 10, 20, 30. You know what? Let's use the one that I actually just wrote there. 0, 2, 4, 4, 10, 42, 79, 101, and 200. There we go. And let's go ahead and write a binary search, recursive binary search version here. It's still going to be integer. The return type is still going to be int because we're going to return the index at which we found it. I'll call it binary search. Right? Call it what it is. It takes an array and the size of the array, or const int star arr. And you could do the size, but remember over here I was changing the size. I really wasn't changing the size of the original array. I was changing the range in which I was searching. So instead of looking at the size and passing in the size, which is kind of irrelevant after that first iteration, I'm going to want to pass in two variables that say I'm searching between I and j. Right? So let's just pass in I and j. You're searching by looking from I up to j. Okay? Now, what's the first thing that you do when you've got a recursive function? You got to make sure that you eventually stop your recursion, so you need your base cases. Right? What's our base case here that we already identified? When the array has gone down to a size of 0, we stop. So here's my I, here's my j. Right? One of the they're coming in until they finally meet each other. And here, when they meet each other, that's an array of size 1. So what happens when there's an array of size 0? I and j have gone past each other. So I'll go ahead and put that into an if condition. If I is greater than j, right, then they've passed each other. So here's I, here's j, right? Initially I'm going to start this down here, binary search on array. Where do I start with the left one? 0. And what about the index here? This is 0, 1, 2, 3, 4, 5, 6, 7, 8, right? So I is less than j. When they've passed each other, when I is greater than j, then no such element exists. The array is of size, and again, it's not really the size, 0. So what should I return in that case? You didn't find what you were looking for. What did we return before on an index-based find? What did we return? -1. So we'll return -1. Remember, that's our base case. That's when we no longer do any recursion. Okay? Else, now we're going to have to determine, is it the middle element? And if not, then we need to recurse on the left-hand side or the right-hand side. Right? So what I'm going to do is, how do I find that middle element, first of all? The middle element initially is going to be 0, 8. Well, it was, the middle element was 10, which is at index 0, 1, 2, 3, 4. Right? How would I have gotten that? If I've got a left index, think about on the number line. If I've got L right here, or I'm using I and J, and there's J, how do I get M? How do I get that one in the center there? Oh, you just computed there what? If I've got a number on the number line here and a number on the number line here, what's the thing in the center? It's their mean, their average. Right? So all I need to do is compute int m is equal to I plus j divided by 2. Okay? Now, a couple of caveats here. It is common to present a binary search using that idea. In practice, that's terrible because you risk overflow and underflow. Don't worry about those level of details. If you are interested about those level of details, read the book. Okay? Also, the second thing that we have to take into account here is, what if I plus j is not even? What if it's not even? So it's say 5 plus 2, 7. 7 divided by 2 is 3.5. So you're going to look at the 3.5 element. Does that sound right? Where do you want to look instead? You want to look at the 7th one. We get that for free. Why? Because of truncation. Good. Right? So I've got my middle index. Right? M is the middle index. Right? And again, caveat emptor here, this is not the way to do it in practice. You would want to instead do something else to not risk overflow. Okay? If the key value, oh, and one other thing I forgot to pass in was the actual thing that we're searching for here, int key, right? So if the m, a sub m is equal to the key element, hey, great, we found what we're looking for. We found our needle in the haystack. We return what? Well, where did we find it? We found it at index m, right? Else if. Now here's where the other condition comes in. If the key element that you're searching for is less than the element stored at a sub m, then we need to recurse on the left hand side, or the left partition hand side. I'll go with that. Right? In other words, we're going to make a recursive call to this function. We just need to figure out what parameters we need here. Right? Let me go ahead and go back over here. And let's think about that first recursion first of all. So let me go ahead and come on. I meant to go that one. There we go. All right. Let's think about that first recursion. 0, 2, 4, 4, 10, 42, 79, 101, and 200. Right? Here's where m. This was index 0 through 8. This it was index 4. 0 plus 8 divided by 2. Right? So this was our a sub m. Right? I need to recurse on the left-hand side. So what indices would I pass into that recursive call? 0 through 3. What if I had recursed on the right-hand side? I would pass in 5 through 8. Right? Before, this was I and this was j. So I need, if I'm recursing on the left-hand side, which one of these do I need to update? If I'm going to the left, I need to update j to 3. If I'm going to the right-hand side, I need to update I to 5. Right? So I just need to update one or the other depending on which way I'm going. If I went to the left, I stays the same. Now, in general, if I've got I, j, and m, what do I update j to? What is this guy right here? M minus 1. Good. It's not m. I've already searched for m. Right? I already looked and see, oh, that's not what I'm looking for. Right? What do I search for if I'm going to the right-hand side? What is this guy right here? This is m plus 1. Right? So, codify that in your code. Right? You pass in the same array. If I'm going to the left-hand side, I is unchanged, but then m gets j gets updated to m minus 1, and the key doesn't change either. Right? Else if, and I'm going to put the condition in here, even though it's not necessary because it's one of these three items, right? It's either equal, strictly less than, or strictly greater than. But if the key is greater than, then I will recurse on the right-hand side. Right? Binary search of array. Now I gets updated to m plus 1. J stays the same. The key stays the same. Okay? And let's go ahead and capture this. Int index is equal to, so printf, oh, and then I have to search for something. The first thing we searched for was 10, so let's make sure that that works. And you know what, let me put this into a variable so we can print it out. Int key is equal to 10. The value %d was found at index %d, and the line. All right, so if I didn't make any mistakes here, this should work. I need to pass in the key. So the value key was found at index with a comma. Ooh, let's find out if this works. It should output that it was found at index 4. Then what's wrong? Oh, there's a simple fix. I won't call it array. I'll call it A. Oh, and then I did call it array somewhere. A and A. I just have to be consistent on my naming conventions. There we go. Oh, I've still got a hello world in there. Value 10 was found at index 4. Awesome. It worked on the first try. Tag it, bag it, and go home? No. What do you need to do? You need to test. Right? What's another thing that we should test for? Can it find the thing at the end? 0? 0 should be found at index 0. And it was. What about the thing at the end, 200? 200 should be found at index 8. Okay, so I can find the elements at the end. Can I find an arbitrary element? Maybe, I don't know, 79. And that should be at index 6. Ah, it works. Right? I'm convinced it works. What else should I test, though? Something that doesn't exist, right? 42 exists. 300. This should report that it's a negative value, right? That I found it at -1 because that's my flag value used to indicate an unsuccessful search. Excellent, right? Excellent, first try. All right. So I won't bother. I mean, I'll put this in the notes for you, but it's in the book as well. Let's go back to the notes over here, and here is our implementation. There we go. It's a recursive implementation, right? It's not that bad. Again, it's not that bad of a recursion. Very low risk recursion here, but still, it seems icky to me, right? Let's get rid of the recursion next time, though. Right? But what I want to do for the remainder of the time here is I want to compare these two, okay? I want to give a justification for, is this better? Right? Because that's what I started this entire discussion on. Well, linear search was great, right? It found what we were looking for. Why do we need to exploit this sorted structure here? How much better is binary search than linear search? Okay, and that's what I'm going to spend the rest of today's time with, on analysis. Okay, so I'm going to look at this at a couple of different perspectives. Suppose you have an array of n elements. Okay, we're going to look at how many how much work each one of our algorithms performs. Right. So work in this case means comparisons. How many comparisons does linear search perform to search the given array? Right. And again, I'm going to give you a couple of perspectives here and then a couple of sub-perspectives here. You could get lucky with linear search. Here's your array. The first thing that you look at, oh, that's the needle in the haystack. You just stumbled over it by mistake. It was the very first one. That's the best case scenario, right? So the best case scenario is that you find the key at the first element. How many comparisons, if I got lucky and did that, how many comparisons would I have made? Yeah, one comparison. Great. Well, let's think about the opposite. What's the worst case scenario? It's what? That you find it always. Where are your keys? They're in the last place that you look. Where's the key? It's in the last place you look, right? So the worst case scenario, you find the key at the end of the array, right? How many comparisons, or you don't find it at all, right? You exhaustively searched it, the entire array, and never found it. How many comparisons in that case? N comparisons. If you've got n elements and you need to compare this key to every single one of them, one comparison each, you needed to make n comparisons. Okay? Well, the first one is the optimist. The second one is the pessimist. And for the record, all computer scientists are pessimists, so usually you do look at the worst case running time of algorithms. But let's go ahead and make a compromise. What would a compromise between the best case scenario and the worst case scenario be? Something in between, something average, right? What would the average case scenario be? Well, I'm not going to get into it because real rigorous average case analysis of this would require putting a probability distribution on the success of search, along with an opposite complement probability distribution of an unsuccessful search, blah, blah, blah. You'd sum them all up, use Gauss's formula, and at the end of the day, it comes out to be almost the same as the naive approach. So naive analysis would be, well, you take the best, you take the worst, and you average them. So the best is n comparisons. The worst is n comparisons. The best is one comparison. And so taking an average of those two would just simply be divided by 2. I'm going to go ahead and say that this is approximately, n divided by 2. Forget about that plus 1. I don't like, again, another admission here is computer scientists do not like dealing with lower order terms. Forget about it, right? So, n divided by 2. In fact, we don't like that divided by 2 either, right? Sorry. Is there that much difference, though, between the worst case? First of all, can you always assume the best case? Is that the best way of looking at these things? Oh, yes, always be the optimist, right? Probably not. But you might have an argument that, well, you can't always be a pessimist either. But what's the difference between n and n squared? So again, for this, let me go ahead and go to this and, come on, okay. That's as bright as it's going to get. Let's go ahead and graph those functions. So instead of the x-axis, I've got the n-axis. And if you graph n, it looks like this. Right? This is n. It's just a linear function going up. But what does n divided by 2 look like? Little slightly less slope there. That's n divided by 2. Looks like that. What's the difference between these two functions? Only difference here is this 2 in the denominator, or the 1/2 out front, right? How would you, what would you call this, and I already said it, what would you call this function here? How would you characterize this? Versus, say, this function. If I said it was n squared, you would call that a quadratic function, right? Well, what's this? It's a linear function. What's this? It's also a linear function with just a different coefficient out front. Gee, where do we get the name linear search then? Right? This is why it's called linear search, because no matter how you look at the behavior, it's going to have linear behavior. What we're looking at here is the size of the array grows. And what we do here is the number, and on the x-axis, this is capturing the number of comparisons. So as we grow the input size here, the number of comparisons also grows. And I don't want to bring calc into this unnecessarily, but what's the growth rate of both of these functions? If you were, okay, let's do calc. What's the first derivative? The first derivative gives you the rate of growth of a function. What's the first derivative of n? What's the first derivative of n divided by 2? 1/2. Characterize those. They're both constant. right? They both basically have the same rate of growth, okay? So, again, I didn't mean to get nasty calc involved here or not, but basically the takeaway here is that both the average and worst cases are linear, right? Okay? But what about binary search? Binary search? What is its behavior like? So again, I'm going to go do a derivation here, and again, this is just going to be algebra though, right? Algebra and maybe some log functions. So jog your memory of, jog your memory of all your logarithm functions, okay? What I'm going to do is I'm going to simply draw a table. At the start, the size of the array is n. We make one comparison to either find the element or say that we need to go to the other side, or the left side or the right side. So I'll keep track of the number of comparisons. We make one comparison. That gives me, how big is the size of my array now? N divided by 2, because I cut it in half basically. It might be plus or minus 1. Don't worry about that. All right? I make another comparison to cut it in half again. What is n divided by 2 divided by 2? N over 4. Let's make another comparison to cut it in half again. And I won't write it ugly like that, iterated division or whatever. Now it's n divided by 8. Make another comparison, dot, 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 dot. Keep working it. N divided by 2 to the k. Because these are, and I didn't write it, but there's 1. There's a power of 2. It's just 2 to the 0, 2 to the 1, 2 to 2 squared, 2 to the third, dot, dot, dot. At the kth iteration, you have an array of size n divided by 2 to the k, and you make another comparison, dot, 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 dot. When do you stop? When the array is of size 0. That's not going to work out for our mathematics. So, and when we go into that last one, we actually don't make any comparisons. So I'm going to stop short at 1. And then we make 0 comparisons there, right? Or 0 or 1. I don't care. I'm interested in what is the total number of comparisons. Well, that's easy. 1 plus 1 plus 1 plus 1. How many 1s are there? That's the hard part. This is the general formula. When this becomes 1, then that's when we stop. That tells you how many rows there are. So all we need to do is solve for n to the 2 to the k is equal to 1. Okay? Now here's where the algebra comes in. Well, this is going to be n is equal to 2 to the k. You bring the denominator onto the other side. How do I solve for k? That's what I want to know. How many iterations are there here? How many rows are there here? How do I solve for k? Log. Now, you immediately said log base 2 of n is equal to k. Log base 2 cancels with 2. You might have been tempted immediately to say, oh, how do you get rid of exponentials? You take logarithms. Well, apply the natural logarithm. What would that have looked like? That would have looked really ugly. ln of 2k is equal to ln of n, right? ln of 2, what is that? Pull out your calculators, who cares? That's the natural log. This is our natural log. We're computer scientists here, computer engineers, and related. Our logs are log 2s. Why? Let's just take a little diversion here. Why is it that the natural log is the natural log? What is the natural log? What is the base? It's e. So why is e natural? What's the first derivative of e to the x? E to the x. That's why mathematicians call it the natural log, because it's the value at which the base, when you take the first derivative, the second derivative, the third derivative, doesn't matter how many derivatives you take, you're never going to get away from e to the x. On the other hand, what is, here, I hesitate to do that. Again, I don't like getting calc in this course. What's the first derivative of 2 to the x? Who knows, who cares? You change the base and then you take the derivative of e. I'm not even going to do it. Right? E is natural for mathematicians because they like nice, clean formulas that they can take this big irrational number and put it into a symbol e. That's not natural for computers. Computers, log base 2 is natural. Why? Binary, zeros and ones. We have different bases. For humans, right, like human music and such, what is their natural base? 10. Why? Because we have 10 fingers and 10 toes. Meet the aliens next year and they've got 11 fingers and toes, then they probably worked in base 11, right? So it doesn't really matter because logs have the change of base formula. This is what I'm getting at right here. How many iterations are there? How many ones are there? Log base 2 of n. That takes us to our final analysis here. Right? There we go. So binary search, it only requires the derivation as it was on the white paper and in the book. Derivation. Okay, I don't know how to spell derivation. There we go. Cut and paste. All right. It only takes about log base 2 of, and I'll make it look pretty here, n comparisons. In fact, log base 2 is our natural base. So if you ever see log, usually it means log base 2. Right? Without, if you see ln, of course, that means the natural log. But our natural log is base 2. I don't have my, where's my nice, pretty picture? Where did it go? Oh, well. All right. We'll draw this again then. All right. Go back to the .cam. So linear search looked like this. Right? Here's n, or n divided by 2. What does log look like? Log base 2? Well, it doesn't start at 0. It goes way down here, but who cares? What does it look like? It's definitely under this, right? What's the growth rate of this? Again, I hesitate to bring calculus into it, but since I already did it, let's go ahead and do it again. What is the derivative of log base n like this? Don't worry about it. I'll tell you. 1 over n, natural log of 2. But forget about that. That's what I want. 1 over n. What's its growth rate? The growth rate over here was 1 or 1/2. What's the growth rate of this? What happens when you get bigger and bigger arrays? The growth rate goes down. It's diminishing, right? So in other words, this will never catch up to this. How much better are these things? Well, according to the rate of growth, you go from a constant down to a diminishing, or you go from n down to log n. That's an exponential improvement, right? And exponentials are huge, right? If I say that you can do exponentially amount of less work on your last assignment, you're going to do it, right? That's a huge difference. Let's put that into perspective. Again, a couple of ways of looking at this. Suppose you have a database of 10 to the 12, i.e., how big is that? That's a trillion, right? You have a database of that many elements. Right? And by the way, that's not that big. On your last assignment, you are going to be working with a database of about, I think I cut it down to a few million. A billion, trillion, that's a million is going to be a trillion. But that's not that big, right? It's very easy to create a database with a trillion elements, right? It's not that big of data, right? If unsorted, you would have to use linear search to find a particular element, right? So let's even be generous here and say that you get to do the average case scenario where it's going to be 1 trillion divided by 2. Well, still, that's what is that going to be? That's 500 times 10 to the 11th. There we go. In other words, this is 500 billion comparisons. Okay? If sorted, and in databases, we call this indexed. That is indexed. Then you can exploit the sort using binary search. How many comparisons would you end up doing in that case? So you would end up doing log base 2, I'll be explicit, of 10 to the 12th. Oops, there we go. Okay, how big is that? And if you need some parentheses, I'll oblige. There we go. How big is that? And now pull out your log identities. What can you do to that 12? You can pull it out front. Log base 2 of 10 is about how much? Slightly larger than 8, so the log base 2 of 8 is going to be 3, so it's 3 point something something, right? This is actually less than 40. Right? So 500 billion comparisons, 500 billion operations versus 40. Right? Which one are you going to do? Binary search, right? That is going to be blazingly fast. There is no comparison, right? But here's another way of looking at it, another perspective. Right? Suppose you double the input size of an array, right? That is, you go from a size of n, right arrow, into 2n. There we go. And misspelled perspective. There we go. So suppose that you double the input size. You go from 1 billion to 2 billion, or you go from 100 to 200. I don't want to look at any specific numbers. I just want to look at general numbers. Okay. What about linear search? Linear search. The number of with linear search, the number of comparisons goes from, and close this, to up 2n up to, since it's linear, what happens? It goes up to, well, 2n divided by 2, which is just n, right? In other words, what would you call that in plain old English? It doubles, right? The number of comparisons doubles. You double the input size, you double the size of the array, it doubles the number of comparisons that you're going to be doing. What about binary search? Right? You go from log n, log base 2 of n, there we go, to, I don't want to have to retype that, so let's go over there, 2n. One more log identity and then you're free of log identities for the day. What do you do with log of a times b? You split it up into 2 logs, and it's going to be the addition, right? So this is equal to log base 2 of n plus log base 2 of 2. There we go. I wanted to write them like this, okay? What happens to that log base 2 of 2? It's just 1. So this is equal to log base 2 of n plus 1. So how many more comparisons did you end up doing? You doubled the input size. You went from 1 trillion to 2 trillion. You only do one more comparison. You go from 850 million to, you go from 800 million to 1.6 billion. And the number of additional comparisons that you make is 1. Right? And that's the power of logarithms. Right? It's exponentially faster. One last perspective I'll give you on this is probably very relatable. It's in the book. Let's see. Hopefully I can find it. Okay. I'm going to have to look in the searching and sorting. Come on, where is it? Searching. There we go. And it's a screen cap from my old Windows machine. Come on, where is it? Darn it. Nope. There we go. Let me go ahead and zoom in on it and bring it over here. There we go. So one day I was searching, this is back when I actually had a Windows machine. I believe this is Windows 7. I noticed that it gave me this, it's not an error message, but it's an end user message. And I was searching for a file. I was searching for a particular file on my computer, and up came this. Searches might be slow in non-indexed locations on your C drive. What does that mean? Non-indexed means non-sorted, right? So searches might be slow if the information about your file system is not sorted. Why? Because it's forced to use linear search. On the other hand, if you've got a computer that goes through, and I've got a Mac now, Mac users will notice this file, this hidden file, this .ds store file. You know what that's for? In the background, your operating system is going through your file system all the time, indexing things, searching for things, pulling out keywords, putting the metadata into that file, so it doesn't have to do linear search. You search and it becomes really fast because it's already indexed, it's already sorted, and it's exploiting binary search. Right? Think about the internet. Think about going to Google. You make a live Google search. Do you think it's doing linear search across the entire internet? No, it indexed things. It indexed them in some storage, and then it's using a fast lookup algorithm. Maybe binary search, maybe something.